Suppose that x is a random variable on a probability space, and it has distribution function fx defined as x is less than or equal to little x for all real x. Well, there's two different probabilities that we could get from this. One, because there is a probability space, we could get the induced measure, which is just the probability of x inverse on A. So Pxa is Px inverse A. The second one that we could get is from the distribution function, and it's the Lebesgue-Stieltjes measure corresponding to this distribution function, which we call mu fx. And what this question is about is showing that these two things are the same. So the way that we do this is we'll first look at sets of the form minus infinity up to x. These are the sets that induce the distribution function from the probability. And so we know from the Lebesgue-Stieltjes assignments that mu fx minus infinity up to x is the distribution function fx of little x. So that was true by our assignment of the Lebesgue-Stieltjes already on S1, the semi-algebra. But we also know that the induced measure satisfies Px on these sets minus infinity up to x is equal to the probability that x is less than or equal to little x, which is equal to the distribution function. So these two probabilities do agree on this collection of sets from minus infinity up to x. Now this collection is not necessarily a semi-algebra, but it is a pi system. This pi system does not necessarily contain the whole set, the real line. However, we can just add it in since both of them are probability measures, so they both have to have assigned 1 to the whole real line. And so in this way, we have a pi system that includes the real line, and they are the same measure on this pi system. Just to establish that it really is a pi system, if you took minus infinity up to x and intersected it with the whole set, you'd get minus infinity back to x again. But if you took minus infinity up to x1 and intersected it with minus infinity up to x2, you get minus infinity up to the minimum of x1 and x2, which is still in that set. So we see it's a pi system. The other thing to note about this pi system is the sigma algebra generated by this pi system is the Borel's. Well, this comes from the general lemma in the notes. And so now all we need to do is to note the following corollary of Dinkin's lemma to complete it. Suppose that we have a pi system C of subsets of the event space F with whole space S, in this case R, in C, and mu1 and mu2 are measures defined on F that are equal on C. Then in fact mu1 and mu2 are equal in sigma C, and from above we just noted that sigma of C is the Borel sets on R. This completes the proof. However, one could also see that by just simple additivity, you could go from this pi system to the semi-algebra S1, and then we know how to go from that semi-algebra to the algebra, and we know by Carathy-Dory-Hahn that you have unique extension beyond the Borel's.
Dear U of A students, while Mike has supplied the content for these videos, there is significant unpaid effort that goes into producing these videos. The folks here at Step by Step Probability are family people with young children that no longer attend school due to the COVID shutdown. Instead of spending time with our families, we made arrangements to continue producing these videos for you. In these uncertain times, it would be very encouraging to see your support through our donation button at the top of the website. Any amount is encouraging and appreciated. Please donate if you can. Thank you and keep safe.